Everyone, the topic of this video is reciprocal unit cell. This is the first video I'm uploading in my channel, and there will be videos that follow up on condensed matter and also on the topic of reciprocal space, the physical significance. But in this particular video, we'll be only seeing the basic mathematical structure so that you can actually pick up a textbook and not be scared by what's written in it. Like I used to be scared when I first started reading physics books on my own. I think everybody who has at least covered grade 12 in school or high school knows what a crystal structure is. A crystal structure is a three-dimensional regular arrangement. So what we have is a 3D grid, and at each point in that grid we have a pattern of atoms and molecules, and that essentially builds up our crystal. Now, just like to build any building, we need a stack of identical bricks, right? So imagine that you have a brick and it is defined by three vectors: a1, a2 and a3, and there are three angles here: alpha, beta and gamma. Notice there's something important to note, that these angles need not be 90 degree. In the basis space of A1, A2 and A3, we can identify 3 points: O given by 0, 0, 0, A by 0, 1, 1 and B by 1, 1, 1. We can identify all the corners of the block by taking linear combination of the three basis vectors. The linear combination is given by a vector called T, the translation vector, given by n1a1, n2a2 and n3a3, where n1, n2 and n3 are integers that can range from 0 to infinity. Notice that we can go from the point 0, 0, 0 to 1, 1, 1 by taking n1, n2 and n3 as 1, 1, 1 respectively. Such a collection of corner points actually gives us the lattice, and each point of the lattice can be reached from another using the translation vector T. Now, if we take the brick, it's what we call a unit cell. A unit cell is the smallest repeating unit in a crystal. I think you have heard this definition 10 million times in school. The entire lattice is generated by the repetition of this unit cell in different directions. Now that we know about the basics of the conventional unit cell, let us dive into the topic of today's video, the reciprocal unit cell. The concept of the reciprocal unit cell is rather abstract. The vectors that form the reciprocal cell lie in the reciprocal space. Now, this space has two features. The reciprocal space is actually an imaginary space where planes of the atoms in the direct space are represented by points in the reciprocal space. And second, all lengths in the direct space is actually inverse of the length in the reciprocal space. Observe the following unit cell. It is again made up of three basis vectors: A1, A2 and A3. It has the following planes: 0, 1, 0, 0, 2, 0 and 0, 1, 1. I hope all of you are familiar with the concept of Miller indices. If not, I suggest you go and take a look at it. Just Google it up. It basically talks about where the plane cuts or makes an intercept with the unit cell. Consider the above 3D figure. Now if you flatten it into a 2D figure, it would look something like this following cartoon. Notice the planes 0, 1, 0 in the 3D figure and the planes 0, 0, 1 in the 2D and the 3D figures. Note that if we have a set of parallel planes in a lattice, then the distance between the planes are given by the following formula of 1 by d square. If the length of the unit cell is same, then we can simplify the formula further by taking a, b and c as a. Can we get an inkling of a reciprocal space from a direct space? For that we will do an exercise. First, we will choose an origin at some arbitrary point inside the direct lattice. Here, the direct lattice is a unit cell, and we have chosen a point O, right? Then, what we will do is we draw normals to each set of parallel planes in that unit cell or the direct lattice. Here, the parallel planes that I have taken are 0, 1, 0, 0, 2, 0 and 0, 1, 1, right? They're stacked on top of each other. And the direction of the normals are given by square brackets, the Miller indices of that particular plane. For example, the plane 0, 1, 0 will be represented by the normal square bracket 0, 1, 0. I suggest you look up direction and plane Miller indices in Google once. After we have drawn normals to each set of parallel planes, what we will do is to determine the length of those normals. Now the length of those normals will be given by sigma. Sigma as in 1 by d, where d is a distance between two planes in a parallel set of planes. For example, the distance in case of 0, 1, 0 plane will be 1. In the distance in case of 0, 2, 0 will be 0.5. The distance for 0, 1, 1 will be 0.7071. Now what we will do is take an inverse of these. When we take an inverse, the sigma values that we get are sigma 0, 1, 0 as 1, sigma 2, 0, sigma 0, 2, 0 as 2, sigma 0, 1, 1 as 1.4136. Now the end point of these normals actually form points in the reciprocal space. Okay, we had seen a point earlier where we had said that if we take a plane of atoms in the direct space, then we can represent that plane of atoms as a point in the reciprocal space. That's exactly what we're doing here. A plane of atoms, say 0, 1, 0 in direct space, is represented by a point at a distance of sigma 0, 1, 0 from the origin in the reciprocal space. Just like we had a translation vector t in the direct space, we also have a translation vector to go from one reciprocal point to another called g, which is given by h b1, k b2 and h b3. b1, b2, b3 are the basis vector in the reciprocal space. We will come to that in the later videos in detail. Let us define three new vectors denoted by a star. It's the same as b that I've used above, used to represent the reciprocal space. AI dot product with aj star gives us Kronecker delta ij into 2 pi. Now this 2 pi represents the periodicity in the direct space. We will come to this in the later videos. Note that AI represents the vector basis vectors of the direct space and aj star represents the basis vector of the reciprocal space. Most of you must be familiar with the fact that Kronecker delta ij is equals to 1 for I is equals to j, and Kronecker delta is equals to 0 for I not equals to j. This particular formulation can be expanded and written in a simplified format as a1 dot product with a1 star gives us 1, as a1 a2 star gives us 0, a1 with a3 star gives us 0 as well, and similarly for the rest. From the definition, we find that a1 star must be parallel to a1 and perpendicular to the vectors a2 and a3. Now, if a vector is perpendicular to two other vectors, then it must be parallel to the cross product of those two vectors, and that is what we come to in the next step. a1 star is equals to k a2 cross a3, where k is nothing but a proportionality factor. And similarly for a2 star and a3 star, what we observe is that a2 cross a3 will give me an area, and a vector normal pointing in the A1 direction, right? What we do is insert the A1 star into the first equation with the Kronecker delta, and we arrive at the following formulation. Simplifying it, we find that K is equals to 2 pi times the volume. This volume is actually the volume created by the basis vectors of the unit cell in the direct space. You will find that L and M are equal to 2 pi by V as well. Thus, we can write A1 star, A2 star and A3 star as the follows. But it's very important to keep in mind that the dimension of each of these vectors is inverse to that of length, and the direction of these vectors actually points towards A1. For A1 star it points to A1, for A2 star it points to A2, for A3 star it points to A3. Here are some other interesting facts about the reciprocal space in the direct space. If the direct space is given by A1 dot A2 cross A3, this is actually the formula of a parallelepiped. I think a simple Google will help you with that, or you might be already familiar with this. So the volume of the reciprocal space will be given by V dash, where B1 dot B2 cross B3. Like I said, I'll be using B and A star interchangeably. I used A star earlier because majority of textbooks actually use it in their formulations, but there's nothing special about it. Now if you simplify this B2 cross B3, what we find is the following. On simplifying this further, we find that the volume in the reciprocal space is actually equal to 2 pi cube times volume of the direct space. The last interesting factor with which I'll conclude this particular introductory video is that the reciprocal of a reciprocal space actually gives us a direct space. Now, if we use the formula that I had given above for A star is, let's say A1 star is 2 pi A2 cross A3 by V. If we use this formulation and insert reciprocal basis vectors inside them, what we find is that on inserting B2 and B3, we end up with A1. Thanks everyone for listening to my first video. This is my first attempt at YouTubing. Let's see how far we go. Bye.